Hello, everybody. I'm going to go ahead and get started. First, I will introduce myself. My name is Derek Parker. I'm a senior software engineer at a company called CoreOS. If you haven't heard about them, I'll talk about them briefly at the beginning of this talk in a little bit. And what I'm going to be talking to you folks today about is how to debug Go programs with a debugger called delv. Delv is a project that I started roughly 3 or 4 years ago at this point, and has grown into one of the more useful and widely used debuggers for debugging Go programs. Maybe? Okay, we're good. So as I mentioned, I work at a company called CoreOS. Now, is anybody here familiar with CoreOS? A little bit? Cool. For those who are not, it's somewhat relevant, as this is not exactly relevant to my talk, but relevant to the conference perhaps, as this has a lot of cloud elements. So CoreOS is a company. We're based out of the Bay Area. We also have offices in New York and Berlin. We maintain our own distribution of Linux called CoreOS Container Linux. It's a lightweight Linux operating system meant to run containers. We also do a lot of open source projects within the community, which I'll talk about in the next slide, and do a lot of work with Kubernetes. So as I mentioned, CoreOS maintains a Linux distribution called Container Linux. Super lightweight, meant for running containers. We also have several other open source projects, such as etcd, which is a distributed key value store that backs projects like Kubernetes and other things. And also Rocket, which was our container runtime engine, which we have since donated to the CNCF, so it's not really under our umbrella anymore. And as far as our enterprise products, we have Tectonic, which we call our enterprise distribution of Kubernetes, which is something that I work on day to day, and Quay as well, which we pronounce it Quay. I think it's properly supposed to be pronounced Key. However, it's a hosted container registry. Okay, so enough of the corporate sponsorship bit of this talk, and on to what I came here to discuss with everybody. So again, I'm going to be talking about a project called delv. It's a Go-specific debugger that I've been working on for quite some time alongside one co-maintainer of mine. Now, I kind of want to get a feel from the crowd as far as how many of you folks are day-to-day Go developers? Okay, so a handful. How many are Go enthusiasts or aspire to be day-to-day Go developers? All right, cool. How many of you folks have experience using debuggers? Anything from like GDB to lldb or anything like that? Cool, perfect. So a good chunk of the crowd. And that's good, absolutely good background to have. Now, just so that I can kind of gauge the crowd and who I'm talking to, how many have actually heard of delv before this talk? Okay. A fair amount, some people who are pretty new to the project. Great, so I think this talk is going to provide a lot of useful information from everybody, from the people who have used delv before to the people who are just learning about it for the first time. So the structure of this talk is such that first I'd kind of like to introduce delv a little bit, talk about what it is for those who are unfamiliar with it, why the project exists, some of the goals of the project, some of the non-goals. And then from there, I kind of want to take everybody through a journey, kind of like a deep dive journey into some of the more possibly esoteric concepts, but concepts that are important nonetheless for understanding why Delve is so different from GDB or lldb, and specifically what makes Go so different that it requires specify like a specific debugger in the first place. What makes it so unique? What's so different about the programming language that it can't be paired with a traditional debugger and find success that way with trying to figure out what's wrong with your code? So to introduce Delve a little bit, the project is written mostly in Go. This is important because I think having the project that is used for Go, written in Go, encourages a lot of contributors from the community, and has so far. It tends to be debuggers are kind of a weird, esoteric project, so it can be a little bit difficult to attract new contributors and things like that, but hopefully there's a few people in this crowd who might want to write some code against it or something. And I say mostly in Go. There are a few CGO aspects to the program, and that's mostly when dealing with some of the lower level aspects on the Darwin mock kernel, where interfacing through Go is problematic, and we have to dip down into C to make some of the lower level syscalls to get coordination with the kernel to actually work when we're dealing with the manipulation of your process. Specifically the manipulation of the execution of your process. And aside from that, aside from some of the lower level features, if there's folks who are interested in contributing to this type of project, I'll be hanging around for a little while. There are some higher level things as well that people can help out with. So the debugger runs on most operating systems, Linux, OS X, Windows. The plan is to expand to more operating systems as we get more, as we iron out most of the actual features that we want, the core features. We want to continue to expand to other operating systems. Basically, our support matrix should be anywhere that Go runs, Delve should be able to run. The only thing that makes it difficult is debuggers being such a low-level piece of technology. It's very, very tied to the operating system, the kernel, and the type of hardware that you're running on. We try to abstract that away as much as possible, but it is what it is at the end of the day. As I mentioned, very much tied to the actual hardware that you're running on. So right now, Delve only runs on AMD 64 processors. This is something that we're working to change rapidly, and I'll explain a little bit later how we're going to be able to do this, but we have a system of pluggable debug backends that we can use, so we're planning on leveraging that to be able to expand the types of architectures and operating systems that Delve can run on. So to dig into and continue introducing the project a little bit more, for me, when I first started making this, and one of the main considerations for me as a user of this piece of software, but as a developer as well, is it should be simple to use. And there's a few reasons for that, in my opinion. Most basic is that the Go toolchain is super easy to use, right? I mean, as opposed to using GCC or something else, you have Go build, Go test. It's all very simple, very easy to think through, very easy to reason about. You don't have to provide a ton of compiler flags to get the things that you want, right? Optimizations are enabled by default. It's so simple to use, you really don't even have to think about it most of the time. And that's important for a compiler toolchain, sure, because that's part of your everyday developer workflow, right? You're building your code, you're testing your code. It's part of the cycle constantly. So that tool should not get in your way. But specifically, if you're reaching for a debugger, things are not going your way, right? Your program is not working. You don't know why. You're trying to figure out why. And so if the tool ends up getting in your way, that's only going to add to the frustration, and it's just going to impede you getting on with your day-to-day development, right? You're going to be stuck on this problem longer if you can't figure out how to use the tool to solve the problem in the first place. So simplicity is a main design goal of this project overall. Try to talk a little bit louder, maybe, because I think the mic got cut off. Oh, we're back, maybe? Good, okay, cool. Okay, so one of the features of Delve is that it has a JSON RPC API. This is useful for things such as like editor integration, which I'll get into a little bit more, which I think is a very powerful feature of a debugger. A lot of people like to sit in IDEs as opposed to being at the command line or whatever else. So this JSON RPC API allows for that. And it's a much cleaner and nicer API. I don't know if any of you folks have had to deal with like the GDB and lldb server APIs. It's very low level, very kind of esoteric and can be difficult to use. This is a lot more simple and allows for integration, for example, between browsers. So you could have like a browser-based front end for Delve and so on and so forth. And even just controlling it from your programs, right? It exports this API. You can control it from other programs. It makes it really simple. So if you'd like to learn more about JSON RPC in general, you can find more information on this website. And to enable this API headless mode, this is the way that you would run Delve. So I'll talk a little bit more about this subcommand later, but essentially you would run dlv debug -- headless. It starts the debugger in what's like the server API mode. By default, it picks a random port, but you can use the listen flag to specify a port if you'd really like to, which that could be useful for things like remote debugging. So one thing that's kind of getting in the way of proper remote debugging and is really low-hanging fruit that we just haven't tackled yet is there's no TLS on the connection from client to server. So with TLS, there's no barrier to doing remote debugging. So if you wanted to run the server on a production or integration server or something like that and have it attached to one of the processes you're running, if it panics or anything like that, you'll automatically be dumped into a debug session, and you can kind of explore and figure out what went wrong in an integration, or you wouldn't really want to do it in a production environment, but in an integration environment, it could be really useful. So as I mentioned earlier, Delve also has plenty of IDE integration. How many folks use IDE for day-to-day as opposed to like Vim or something else? A few people. Yeah, so IDE integration with a good debugger is very, very important. A lot of folks who come from like some of the more hardcore IDEs that have really, really good debug integration, like Visual Studio back in the day and things like that, a lot of times they can't live without that integration. You know, it's so ingrained into how they explore their code and everything like that that it becomes a necessity. So with that, the community has contributed a lot of different integrations for Delve. So as you can see, IntelliJ IDE has a Golang plugin. JetBrains Gogland, which is a newer, still work in progress IDE specifically for the Go programming language, has Delve integrated natively. Visual Studio Code has Delve integrated with the Go plugin. Light IDE, and for the folks, Adam as well, and for the folks who tend to be more at the terminal, like myself, Emacs and NeoVim also have support for doing IDE style or in-editor style debugging with Delve. Additionally, there's some alternate UIs for Delve. One of the bigger ones is GDelv, GDLV. That is maintained by the co-maintainer of Delve, Alessandro, and it's something he's been working on for quite some time. If you'd like to take a look at it, there's the link. I could also show real quick just what it looks like. So if you see, you can have, it provides a lot of information all in one screen. So you have like your source code listing, you have the disassembly of the source code that you're looking at, so you can step through the code and the assembly code at the same time to figure out some maybe more difficult or lower level issues. You have the stack trace available to you, all of the locals that are in scope, and as well as further down you can see there's like the actual prompt where you can enter in commands and actually interact with the program that way. So this is just an alternate UI if you're not interested in interfacing with the debugger via an IDE, but you still want maybe a more robust experience. This is a potential solution for that. And as I mentioned a little bit earlier, one of the interesting things about Delve is we have pluggable low-level backends. So what I mean by that is the actual debug server that interacts with the operating system and the kernel to handle all of the process manipulation. So starting and stopping the process, reading and writing from process memory, things like that. And why this is important is because when the project initially started, I wrote the backend for Linux and OS X. The backend for Windows and the port to Windows was contributed by a couple folks at Microsoft. Since then, we've been able to integrate GDB as a backend and lldb. And one of the important things about that is we no longer, if we switch to using these other backends, we no longer have to spend so much time writing our own low-level code to port to other operating systems and other architectures. We can just leverage these other backends simply as kind of dumb APIs to handle some of the lower-level heavy lifting, and get Delve running on more operating systems and more architectures faster. One of the other really interesting things about having pluggable backends is it allows us to do some things that other tools cannot, especially for Go. So I don't know if any of you folks are familiar with Mozilla RR debugger. So a couple people. So essentially what it is it's a record replay debugger. So it's a deterministic debugger. So essentially what it does is it'll run and essentially trace your program and allow you to replay that execution. And that when it replays it, it's replaying everything specifically. So memory layout is exactly the same. Every single branch, jump, everything is exactly the same. So if you really want to dig into a hard problem, this can help out a lot because there's no differences between runs. Every single run is exactly the same, memory layout, etc. And so tracking down difficult problems could be a lot easier. It also allows you to do some time traveling stuff, so you can like step through execution backwards as well as stepping through execution forwards. Since it's all recorded and being replayed anyways, it gives you a lot of flexibility there, which I thought is a really, really interesting feature and something that Delve provides for free simply by having this pluggable backend mechanism. Right, so what makes Delve so special? Why can't we just use another debugger such as GDB or lldb? Even if we use those debuggers as backends, why can't we use them just natively against Go? There's quite a few reasons for this. So I'll dig into this a little bit more later in the talk, but Go has a very different execution model than other programming languages. So a traditional programming language, the smallest unit of execution is going to be the thread, right? And in a sense, that's true with Go. But Go has this other concept of Goroutines, which it multiplexes on top of threads. So that Goroutine being the smallest unit of execution means that it can switch from thread to thread. It can switch around, and it can switch around during the course of you stepping through your code. And this confuses traditional debuggers because they're focused on the thread, not focused on where the actual Go routine is going. So you can be stepping through your code and say you have like 50 different Go routines running the same function. You're stepping through that code, you step to the next line, you think you're on the same Go routine because the code looks the same, but really you're on a completely different stack, completely different Go routine stack, completely different local variables, and it's just going to screw up your debugging session. You're going to confuse yourself, and you're not going to be able to solve your problem. So Delve is able to handle this for you and make Debugging Go a lot more sane. So one of the things that I mentioned is Goroutines being the smallest unit of execution. Now, I'll dig into this a little bit more as well, but Go has an internal runtime scheduler, which takes these Go routines and puts them on different threads and runs them and pauses them at various points during the execution of your program. So one of the things that Delve is able to do is follow those jumps and give you a consistent view of your program as it's executing. And one of the most important things is, like, a lot of the reason why people tend to go for Go, didn't mean to say it that way, is for the concurrency, the easy parallelism, right? Being able to do Go and then execute your function in parallel is extremely enticing and brings a lot of people to the language. So being able to debug those highly concurrent programs is equally as important. So Delve also understands a bit more about how Go types and interfaces work. This is important for just exploring your code, right? So if you want to print out a variable, the variable is an interface. Other debuggers might not be able to really understand that and parse what the underlying actual type of that interface is, or get more information out of that variable to display it to you so that you can explore a little bit more what's going on in your program. It gives you better visual output. Allows for you to do some better, like, type assertions within the debug session. And on top of that, it understands some of the other native Go types that we use day to day as Go programmers, right? So slices and maps. So it understands and it can display for you different parts of the internals of slices and map, like the length and things like that. And within a debug session, there's actually a little bit of a interpreter built in. So you can do things when running print statements. And if I have time for a demo later, I can show this. When doing things like executing print statements, you could do, for example, print my array squares 0 or 1 or whatever, and actually index into the slice. You can reslice from the debug prompt. And you can also read values from maps. So it understands Go maps, how they work, how to read values from them. So you could do, like, my map, your key, and then actually get the value back out of that while you're in the interactive prompt. Which I think stuff like that is kind of small, but goes a long way towards you having a better, actually, like, interactive session with your program, and being able to explore it a lot more reliably. So it understands Go control flow as well. So panic, recover. When you start a debug session, it will automatically set a breakpoint to recover for whenever panics happen. So if you have an unrecovered panic during the execution of your debug session, it's automatically going to stop. It won't just let your program crash. It's automatically going to stop, put you at the prompt, the debug prompt, and let you explore what's going on at that specific moment when your program crashed, which can be very important to try to discover what led up to that. If just the stack trace that Go barfs out whenever you get a panic isn't quite enough. It knows some internal Go debug functions. So there's runtime breakpoint, which I'll talk about a little bit later. It knows how to handle this function. It knows how to, if you set this in your code, it knows how to step out of some of the internals and put you on the next source line where you want to be so that you can continue debugging. It's a lot easier if you just want to set breakpoints visually in your code without having to jump into a debug session and type break and specify, like, a file line or a function name or something like that. Cool. So now we'll get into some more lower level, interesting, fun stuff. So I kind of want to spend a little bit of time digging into the Go runtime because it's interesting to me and explains a lot of what makes Go so different from other programming languages. So we're going to go down the Gopher hole a little bit. So let's talk a bit about the Go scheduler. How many people are familiar with the fact that Go has a scheduler, or roughly what it does during the execution of your process? Okay, a few people. That's good because we're gonna dig into it a little bit. So those who don't know can learn a little bit more. So I thought we were talking about debugging. Why is this important? I feel it's important to discuss overall. Like I mentioned, what makes Go different, and just for everybody to have a general understanding of what's happening when you run your Go binary. You know, if you're trying to debug something, it's super helpful to know the internals and what's really happening during the execution of your process. Because Go is a little bit different and a little bit interesting. It has a lot of different concepts that it abstracts away from you that generally you don't need to think about, but can be really important to know just in the back of your head. While you're writing Go code. So let's talk about some basic scheduler concepts. So the scheduler is comprised of essentially 3 main components. So you have the G, which is the Go routine. You have P, which is the processor, and then M, which is thread. And M actually stands for machine in the scheduler parlance. And so for those of you who are familiar, when you set the GoMax procs environment variable before you're running your Go binary, it actually affects the P part of the scheduler unit. And I'll explain what these do. So everybody's familiar with the Goroutine. That's, you know, the little bit of it's like a interesting little coroutine that is scheduled internally by the runtime. So a processor maps to an actual it's supposed to map to an actual core, right? An actual CPU core, an actual processor running on your machine. And M is an operating system thread. So whenever Go creates a thread for you on your behalf, it manages it internally in the runtime. So threads need a processor context to be able to execute. So the way the scheduler works is an M will grab a processor context. That processor will have a list of Goroutines that are attached to it. So there's a list of Goroutines on each processor and a global list of Goroutines as well. So when an M grabs the context of the processor, it starts pulling off and running these Goroutines. There's also the concept of Goroutine stealing. So if there's no Goroutines to run on a specific processor, the thread will steal from another processor and start running it there. So that's how you get things like Goroutines moving around, even if you don't have explicit context switches in your code, which I'll dig into a little bit later. But it adds to the confusion for traditional debuggers, and that's kind of why I wanted to go into some of this backstory. So context switching. Context switching is so a Goroutine moving to another thread. So this is very important, can confuse a lot of traditional debuggers. It can happen right from under you, and it's sometimes not super apparent when this is going to happen during the execution of your code. So what causes these context switches? Blocking syscalls. So if a Goroutine running on a thread enters a blocking syscall, what's going to happen is the runtime is going to essentially pause that thread, spawn a new operating system thread, and continue the execution of other Goroutines. So that's a case where you can end up like your Goroutine can be descheduled and stolen by another thread or something like that, and you can end up in a weird place. Network I/O. So any kind of blocking I/O call is another potential context switch. Channel operations are another one, and these things are also common as you're stepping through your code. So the potential to be tripped up by these is pretty significant. There's also some primitives in the sync package that that allow you to initiate these context switch. So runtime go sched is one of them. Yeah. So if anybody's interested in learning more about the scheduler, what it does, and what kind of decisions that it's making, you can actually run Go if you're familiar with the Go debug environment variable, you can run this this invocation as you're executing your program, and that'll give you very detailed output of it'll trace what the scheduler is doing, what decisions it's making, why it's making those decisions, so on and so forth. I'll leave that up for a second if anybody wants to grab a picture. Now, the output of that can be kind of weird and hard to distinguish. So there's actually a blog post by a great member of the Go community and great speaker and workshop author named William Kennedy. He has a blog post that goes very much in detail explaining how to interpret this output if you wanna dig in and learn more about the scheduler. All right, so let's switch back. Let's take a deeper dive into Delve and how Delve works. So by default, when you use any of the basic Delve commands, which I'll show later, it does a couple things for you to make your life a lot easier. So it'll compile your program without optimizations. As I mentioned earlier, the Go toolchain will automatically provide optimizations to your code, such as function inlining, registrization of variables, so on and so forth. The state of the world is such that the Go compiler and linker is not able to emit enough debug information for those optimizations currently. We're working with them to improve that. So for the time being, we turn those off to make it a lot easier to debug your binary. And the way that we do that, if you ever wanted to do that on your own, is by providing this flag to Go build or Go install. This is particularly important if you want to run a binary under Delve without Delve compiling it for you. So if you wanted to do like DLV exec, which I'll get into a little bit later. So what optimizations are removed? I'll touch on this a little bit, but function inlining and registrization of variables, excuse me. The main reason for this is the debug information that the Go compiler and linker emits doesn't contain enough information for debuggers to sanely piece some of this stuff back together. So if it inlines a function, it's not really able to convey to the debugger what's going on. If it switches a variable from the stack into a CPU register, again, it's yet unable to fully convey that properly to debuggers. So we just turn all of that off, do stack-based function calls, and remove function inlining as well. So I kind of want to spend a little bit of time demystifying debuggers. I'm always interested in some of the lower level concepts behind how things work, so I want to dig into that a little bit more before I go kind of more into just basic usage of Delve and all of that. So is anybody familiar with some weird esoteric concepts such as what dwarf is? Cool. Fresh minds. So dwarf is the standard for how to express debug information within a binary. So this is any kind of binary, elf, mock, so on and so forth. So by default, it's present in all Go binaries, and you have to provide a flag to actually strip that out. This is one of the biggest sources of contention between this project and Go core, as we're fighting with them to improve this information. So the better this information gets, the better your debugging experience is going to be. So it contains information on variables, the stack, so on and so forth. So there's a bunch of different sections for dwarf. They all contain a bunch of specific information and are useful to debuggers, but pretty much exclusively that. So just to point out a little bit, there's debug frame, which has call frame information. So that's how we're able to do, like set up a function frame so that we can read variables, like arguments that are passed in and variables that are being stored on the stack. We can also use that information for doing things like unwinding the stack and generating stack traces and things like that. Debug info, core dwarf information section has a lot of information about types and variables and things like that. Debug loc has information about different locations within the program and mapping program counter addresses to file line information to be able to show you where you are as we're actually stepping through your program. So just to kind of give you an idea of what this information looks like, so this is a debug frame header. It has some useful information. So CFA is canonical frame address, which is basically just telling you this is the address that of the current stack frame that you're in within the context of the function that you're calling or you have called. So the current call frame is the current function stack frame. So all of the arguments and local variables that it's using are all stored on the stack, and that's how we're able to read and parse that information. And here's an example of an actual debug frame section. So you can see initially when we enter into the function, the canonical frame address or offset rather is 8. So that's 8 bytes. So the stack frame hasn't really been set up yet, so there's really nothing there. As we jump in, we see it grows to 48 bytes. That's because we have to grow the stack, make room for function arguments, make room for any local variables that are being used during the execution of that function. And then as we exit, we see it shrinks again. So this is just kind of interesting information anyways, just to see how a function call works a little bit, right, as we grow and shrink the stack to accommodate variables and function arguments and so on. Likewise, this is a debug info header. Just gives you some basic information about like what dwarf version is used, the pointer size of the particular architecture, which can be useful if you really need to parse it out and don't want to actually guess. And here's an example of debug info. So you can see it's showing like at the very top. I don't know if I have a pointer with this. Oh, sweet. So at the very top, we're specifying a subprogram, right? So fum to print line. It gives you the high and low PCs for that. So this is like the actual like where in memory this code lives while it's being executed. And then this information is stored as like a tree, right? So you have the root of this tree right here, and then you have some children. So the children are like the arguments and return values. And this actually shows a bug in the current implementation of the dwarf, because there's no way to distinguish between an argument and the values that are getting returned. So from a debugger standpoint, it's impossible to know what's being passed in and what's being returned from this function. And this is something that we've been back and forth with on the core team, and I believe it's actually fixed right now in the latest version of Go. So this should no longer be an issue. Cool. So now quickly to move on to some interesting kernel-specific details of the debugger implementation. So on Linux, we use a syscall called ptrace. It's a family of syscalls. Well, it's really one syscall that you can provide a bunch of different parameters to. This is how we control a lot of the execution of the process: starting, stopping, reading memory, writing memory, so on and so forth. If you want to learn more about that and you have a Linux system, you can just run man ptrace and dig into all of the greatness. On OS X, there's a lot of specific Darwin and mock syscalls. The great thing about that is it's completely undocumented. So writing the OS X backend was mostly reading the open source bits of the Darwin mock kernel and just figuring out what was going on. It's a really good time. Windows actually has a really good debug API, and the Windows port of Delve was provided by some folks at Microsoft, so I never had to pay for a Microsoft license, which is really nice. Cool. So what makes Delve different from other debuggers? As I mentioned earlier, it understands the scheduler. It doesn't focus on threads. It focuses on Goroutines. Is able to follow them around, give you a sane debugging experience. As I mentioned earlier, follows Goroutines. Even if you have 100 different Goroutines running in your system, it's always going to stay consistent and follow the same Goroutine as you're stepping through your code. Understands Go types, so it knows about interfaces, slices, maps, things like that. Understands Go compiler intricacies, so it knows what flags to use to build like the optimal binary for debugging. Knows what dwarf information is available and what's not available and how to compensate for that to give you the best debugging experience. And another thing that's unique with Delve that is not with other debuggers is potential integration with the runtime. So our team integrates with a lot of the Go core team to solve some of the tougher problems with debugging Go. And one of the potential benefits of that is getting explicit help from the runtime team to assist Delve in creating a better debugging experience. So having runtime hooks into being able to call functions while you're in your interactive debug experience, which is something that just wouldn't be there with another tool that's more generic and not Go specific. It understands Go developer workflow, so this is just part of it being easier to use. Go build maps to like Delve debug. Go test maps to Delve test. It knows how to build test binaries. It knows how to build normal binaries, and it takes care of all of that for you. It also has some extended functionality that may not be in other debuggers. So it knows how to do tracing, so similar to like dtrust or something like that, where you can do like tracing from outside of your program without having to jump into a debug session. You can do similar things with Delve. So you can run the trace subcommand, provide it a regular expression, and it'll give you output basically whenever any of those functions are hit. As the debug information improves, we're able to tell you the arguments to that function, the return values from that function, and you can just kind of spy on your program from the outside without having to dig into a full debug session and kind of explore that way. Additionally, this is something that most other debuggers can do, but Delve can also debug core dumps. So if one of your processes crashes on an integration or production system, leaves a core dump somewhere, you can use Delve to explore and figure out what happened and how to fix it in the future. I mentioned earlier pluggable backends. One of the most exciting of this is Mozilla RR. I would strongly encourage anybody who's interested in this to check out that debugger and play with it a little bit, and specifically play with the integration with Delve. It's really interesting and super powerful. So I'm going to skip a little bit of stuff on installing so that we can get into some more usage. So all of this stuff that I'm skipping can be found in the documentation in the repo. So I'll just kind of blow past it real quick. So let's dig into how to actually use Delve. So the main command that you're going to want to use during a normal debug session is dlv debug. So what this will do is it expects to be ran in wherever your main package is, right? So it'll compile for you and start a debug session that you can jump into and start playing around with. DLV test, likewise, will do something similar to Go test, but it'll build a test binary for you, because we're all writing tests for our code. So it'll build a test binary for you that's optimized for debugging and allow you to debug your code within the context of your test. DLV exec will run a pre-built binary. So if you have something that's built by a more complicated toolchain, such as like Kubernetes is pretty wonky one to build a lot of the time. You can just build the binary and exec it through Delve as opposed to having to use Delve to build the binary itself. With this, it's good to mention that you should probably at some point try to provide this flag to the compiler just to give you a better debug experience. You can also attach to a running program. So DLV attach, just provide a PID. Delve will attach to that process and begin debugging it. It'll stop it immediately and jump you into a debug session. And then as I mentioned earlier, you have DLV trace. So you can provide any kind of regular expression that's parsable by Go's regular expression engine. And the actual output of this is wrong. It won't do this. It won't jump you into an actual session. It will execute your program, and during the execution of your program, if it hits any of these trace points, it'll print out information about the function. Cool. So one of the last things I want to talk about is some interesting tips and tricks that you can use when in your Delve debugging session that I found super useful and can be really helpful for figuring out whatever's going wrong in your program. So something that I think is really interesting, coming from dynamic languages, I used to program in Ruby a lot, and using pry and being able to put like binding pry somewhere in my source code was really, really cool, and made for a really quick debug feedback cycle. So you can do something somewhat similar with Go. So they provide a runtime breakpoint function. You can just put that wherever you want and run it under Delve and just continue, and Delve will automatically stop and put you on the next source line, ready to start debugging your code. Setting a breakpoint on main. This is something that trips a lot of people up. So since Go has various like init functions and stuff like that, we don't assume that you're always going to want to go straight to main. So we don't set a breakpoint on main for you. So when you start up the process, you're really at the very, very beginning of the process before it's even jumped into main. So a tip is to, if you just want to go to the very start of your process, set a breakpoint on main before continuing or before trying to do any other command, because the initial output could be very confusing because you're lost in assembly world somewhere as your program is actually getting initialized. We get tons of bug reports on that, and so I'd like to clear that up. If you're in a panic, you can print this variable out. This will give you the result of the panic. You don't always have to do this, but this is a good tip. But if the panic breakpoint is hit, it will automatically print this out for you. So it will just automatically let you know what the panic reason was. You can switch to another Goroutine while you're in your debug session. This slide is wrong, but if you type Goroutine and then a Goroutine number, you can switch over. You can show the backtrace. So typing stack will show the backtrace from wherever you're at. So like you're in fumped print line, that was called from this file line in main, which was called from runtime main, which was called from so on and so forth. With that information, you can actually execute commands in another frame. So with that stack trace output, if you wanted to see what was happening 1 or 2 frames above you, you can run frame, the frame number, and then some sort of command. So like ls is list, it'll print out the source code. You could also run like locals or any other kind of command and get information back. You can list Goroutines, and the asterisk will show you what Goroutine you're currently on. You can also provide some flags to Goroutine, to this command, to change the output of this. So here we say user. So we try to show you where in user land you are and try to get you out of like internal runtime land. But if you want to actually see that, you can choose to see that as well. You can list threads. Same deal. It'll show you an asterisk of what thread you're actually running on. Right, this is what I showed earlier, but this is the actual correct slide. So Goroutine to ls, you can execute commands on another Goroutine and see the output there. Print map keys. So as part of the print subcommand, You can say my map, my key, and it'll print out the value. You can print struct members, so it's pretty nice and interactive. You can print slice values, so you can index into slices and also reslice. And there's a lot more. I'm running out of time, so I will just end it there. But if you take a look at the documentation, you'll see all of the different like tool or all of the different commands that you can use within a debug session. If anybody wants to reach out to me, I'll be walking around a little bit, so I can do some kind of like hands-on demos if anybody's interested. And if anybody has any more questions of how to use it or how to explore the debugger. And with that, that's it. Thank you. I'm Derek, and appreciate it.